In this video, we will review at a high level the key concepts behind deep reinforcement learning. This video is part of a 5-part series on autonomous systems. Please refer to the links in the comments section of this video for direct access to the other parts. What are the key concepts behind deep reinforcement learning? Deep reinforcement learning has 3 key components. The first one is that the AI agent will be able to train by itself without the need of formal training datasets. This training will happen through hundreds of thousands or even millions of trial and error cycles. And because, obviously, it's not possible to run those kinds of trial and error cycles on a real-life system, advanced simulations are required to train those systems using reinforcement learning. Before we spend more time drilling into deep reinforcement learning, let's spend a few minutes to look at the more traditional way of training in order to better contrast why deep reinforcement learning is so interesting for many real-life industrial use cases. In traditional AI training, you provide a set of training data being the expected output value for each input value. For deep neural networks training, these dataset size requirements can easily run in the millions of individual data points. And in most real-life business situations, those are just not available. The type of data you'll need for this type of AI training depends on the type of AI that you're building. For instance, if you're training the acoustic model of a speech recognition engine, you'll need to use a recording of people speaking and the associated written versions of those words and phonemes. If you're training an AI model to use it for automatic image tagging, you'll need to provide images of what you want to recognize, such as a banana, a cat, or a dog, together with associated text description of the image. And if you're training a machine translation system, you will provide the text in both the source and target language. In all of those examples, you can see that it would, in most situations, be extremely costly to generate this training data out of thin air. Because it isn't that kind of labeled data that companies usually have access to. In most cases, it will be too expensive to create this data using human resources. Now, if we look at the actual training process, the neural network output will be compared with the expected output. The difference between the expected and actual outputs will then be used to modify the neural network parameters. This process will continue and be iterated for each element in the dataset and over multiple eras until the neural net converges to an acceptable quality level. For reference, an era represents one training cycle that has used all the data in the dataset at least once. With deep reinforcement learning, the AI agent, i.e. the deep neural network, will send comments to the simulator and measure its output. Using the difference between the expected and actual simulator output, the agent will then self-modify its parameters and try again. With this approach, using an appropriate platform, such as the Microsoft Project Bonsai platform, you can run millions of training cycles in a matter of hours. With every cycle, the AI agent learns and gets better until it converges to an acceptable level. An example of a similar approach is when Google showcased how its Go program could learn by playing against itself. In that case, the simulation and the AI engines were two instances of the same AI. Let's double-click to see how reinforcement learning works. With reinforcement learning, the AI developer will define a reward function. This reward function leverages the expertise of process designers and operators to identify what parameters are the most relevant ones and decide whether an AI agent action is optimal or not. This approach of using human experts to help design the AI reward function is one of the elements behind the concept of machine teaching. I would encourage you to check our video on machine teaching linked in the comments section of this video. As previously explained, during training, the AI agent will generate an action that will be sent to the simulator. The state of the simulator will then be sent back to the AI agent. The reward function will then analyze the simulator state and compare it with the optimal one. Using the output of this reward function, the parameters of the agent will be tuned and a new cycle will start again. A typical AI agent training will take between several hundred of thousand to several million cycles. And as depicted on this slide, the agent will use a simulator to train and won't use the actual process that it's supposed to control. This is easily understandable because in most situations, it will obviously be impossible to use a real-life system to train the AI in a trial and error fashion. Simulators are going to be a critical part of any deep reinforcement learning project. And there are several strategies when it comes to developing the right simulator for your system. At the highest conceptual level, simulators can be bucketed into three types of simulation approaches. First, you can use advanced simulation packages that can simulate very complex systems. A second approach, if the system is of limited complexity, is to use the laws of physics and to build a mathematical model of your system for a simulation. With the advent of digital twins, more and more equipment manufacturers are providing those kinds of simulations, and they can be a useful mechanism to get started. For very complex systems that can't be simulated with enough accuracy using either existing software packages or physics-based approaches, the option of building one or more AIs to simulate the real-life system is also a possibility. However, in that case, the question of how to train this simulation based on real-life data can be tricky. This concludes our video on deep reinforcement learning applied to autonomous systems. Please check the other parts of this video series. You will find the links to those parts in the comments section of this video.